Hello and welcome. Today we look at VSEPR for IB chemistry, looking first at this molecule, CH4, methane. First we're going to look at how to draw the Lewis electron dot diagram for CH4. So as you can see here, I have put the carbon atom in the middle, its 4 valence electrons and the 4 hydrogens. I haven't added any lines because the Lewis electron dot structure requires the bonding pair to be represented by a dot and an X. Alternatively, could represent the bonding pairs by a straight line. And this would be your Lewis electron dot structure for CH4, methane. If you take a look at CH4 in the model, here, you'll see that the spatial arrangement of the 4 bonds would put each hydrogen at the tip of a tetrahedron. So this molecular shape of CH4, its molecular geometry is described as a tetrahedral molecular geometry. And we can draw a diagram to represent this tetrahedral shape like this. In this format, we get a better representation of the CH4's tetrahedral structure. And this too can be considered a Lewis electron dot diagram because it's got the 4 bonds. The bond angle here is 109.5 degrees. Here we have another molecular model. This one, H2O. But this one's a little different because it's got 2 lone pairs of electrons here attached to the central oxygen atom. So we will draw the Lewis structure of this in this way. Oxygen with its 2 lone pairs and then its 2 bonding electrons, here 2 hydrogens. 2 hydrogens and 2 lone pairs of electrons. These lone pairs of electrons, highlighted here, push against these bonded pairs of electrons, creating this bent or V shape for the water molecule. So if we took the lone pairs out of the picture, the water molecule would look like this, a bent or a V shape. That bent or V shape is its molecular geometry. But its electron domain geometry requires consideration to be given to the 2 lone pairs and also the 2 bond pairs. In total, you have 4 electron domains, the 2 bonding areas and the 2 lone pair areas. And we could use this type of notation, A to represent the central atom, B to represent the bonding domains, and the 2 bonding domains, and the 2 lone pairs of electrons could have this letter E2. So AB2, E2 to represent any structure that has a central atom with 2 lone pairs and 2 bond pairs. Returning to methane and to follow this system, we would have CH4 and then A, B4, and no E's because there are no lone pairs of electrons in methane. Now let's continue our look at VSEPR, looking at a linear structure and a trigonal or a trigonal planar structure like BF3, boron trichloride. Boron trichloride is not just any other example of something that has 3 domains, 3 electron domains, 3 bonds, but boron trichloride is also an exception to the octet rule. Let's look at its electron dot structure in more detail. I'm not forgetting that Lewis electron dot structures need to include all valence electrons as well. So we need to include all of the valence electrons in all of these chlorines, 8 electrons. So you have BCl3, boron trichloride. A, B3 also you have. And there are no lone pairs. So we represent all molecules that have a central atom and 3 bonds as AB3, if they have no lone pairs. If they have a lone pair like ammonia, then you would have to put an E here with a 1. Boron, of course, is an exception to the octet rule because this is its structure and boron does not have a full octet. And now we come to a case with 2 electron domains, 2 bonds, and another exception to the octet rule. Beryllium is the central atom, and the 2 bonded groups here are 2 chlorine atoms. This is the structure of the covalent molecule beryllium chloride. Be, beryllium in the middle, bonded to 2 chlorines, including the valence electrons again. Chlorine here, BeCl2. This is a covalent structure. A, the central atom, 2 bonds, AB2, no lone pairs, so the molecular geometry of such a structure is linear. Beryllium chloride, another exception to the octet rule also, because beryllium only gets 4 electrons in its valence shell, starting off with 2 and sharing with 2 chlorines, but each have 2. Beryllium chloride, 2 electron domains. Next we look at ammonia, and this too has 4 domains, 3 of which are bonding domains and 1 with a lone pair. So let's start by drawing the Lewis electron dot structure for ammonia. Remember, it's either you have dots and crosses or lines. You can't really mix them. So therefore I'll have to remove all of these dots. A line represents, in the Lewis dot structure, a line represents a pair of electrons. And if we're going with the line format, it's fitting that we also put a line up here at the top. And this would be a valid Lewis electron dot diagram for ammonia. It's got its 4 domains, 3 of which are bonding domains. So we could represent molecules of this type as being AB3 for the 3 bonds, E1 for this single lone pair. Now we want to add the fact that this lone pair of electrons pushes bond pairs to such an extent that the repulsion between the lone pair and the bond pair is much greater than the repulsion between the bond pair and the bond pair. So what this does is it distorts a perfect tetrahedron that you would get in the case of methane into a slightly imperfect tetrahedron with the lone pair pushing the bond pair down just that little bit more and the bond pairs not pushing against each other as much. We have a bond angle here that is less than 109.5 of the typical tetrahedron that you would get. And the shape of this actual molecule, not considering its lone pair, the molecular geometry then, not the electron domain geometry, its molecular shape, if we didn't consider its lone pair, that molecular geometry for ammonia is trigonal pyramidal, which is this arrangement right here. Triangular arrangement, but in the form of a pyramid, as you can see here. You can stand on my hand as a pyramid. And finally, let's return to take another look at the water molecule. It has 4 electron domains in total, 2 bonded areas, and 2 lone pairs. Its entire electron domain geometry is tetrahedral, because if you consider its 2 lone pairs as spaces, then its shape very much matches the shape of methane, which is a tetrahedron with 4 bonded structures. Water is a tetrahedron when you give consideration to its 2 lone pairs. If you don't give consideration to its 2 lone pairs, you will get this bent or V shape. This is the molecular geometry of the water molecule. It's bent or V shape. molecular geometry. But electron domain geometry means you must give consideration to the 4 spaces that contain electrons, pairs of electrons, domains of electrons. And electron domain geometry, tetrahedral, molecular geometry, bent or V-shaped. And in addition to the fact that the water molecule has the bent molecular geometry and the tetrahedral electron domain geometry, we also need to consider the fact that this water molecule is a polar molecule, because oxygen is very much more electronegative than hydrogen. And the shared electrons in this covalent bond are held that much closer to oxygen than they are to hydrogen, creating bond polarity. And of course, this bond polarity allows one water molecule to closely attach to another water molecule in what we call hydrogen bonding. But in addition to bond polarity, the entire molecule becomes polarized. And there's molecular polarity in here as well, because there's a pull of electrons towards this direction entirely. Sometimes you have a molecule like BCl3. And when you have a molecule like this, you realize that there's tremendous bond polarity, because chlorine is very electronegative and it keeps electrons closer to itself. But overall, as a molecule, there's no dipole, there's no molecular polarity, because the pull in this direction, and this direction, they all cancel each other off. So there's no molecular dipole in here. There's bond polarity, but no molecular polarity. Whereas in water, there's bond polarity and molecular polarity.